once again for those who are not there yesterday. This is GDC, University of Nairobi, IoT, yes, in partnership with University of Nairobi Microprocessor Association, together with the Rust community. We are learning Rust for those who are not there yesterday. We did like an outline of what we will be doing. And now I can see we are 10. Without no wasting time, we can begin. I'll invite the lead from Rust community to start. Kiari, if you can hear me.
So I can't hear you. So we start. How are you guys? I hope you're good. Share my screen. So yesterday we covered the course outline. You can find it in the readme of the GitHub repo we are using. The GitHub repo is this. So if you miss the course outline, you can find it in the readme of that repo. Okay. So today what you're going to cover, we're going to do an intro on what drivers are and what they are not, and then we will start to write a bare metal program, and then we'll end it there. And then tomorrow we will start writing a virtual UART. We may cover the theory first, then the actual implementation. So today we are covering intro to drivers and writing a No-std, a bare metal executable or program. Then tomorrow, that's when we start doing stuff related to the UART itself. So let's look at the book. This is the book that we'll be using. It's also found in the repo. So let's begin. So what should you know before doing this or taking this course? Well, you should know nothing. There are no restrictions. You just be proactive. Find a way to learn things. You don't have to know all these things that have been listed here. For example, it's been listed that you should cover till chapter 14 of the Rust book. That's an overkill. As long as you know how to write loops, functions, the rest you can learn along the way. Create management. The project will provide you with pre-made projects, so you don't have to worry about managing a large crate or anything. You can learn it along the way, so don't get discouraged. This one here is an overkill. Chapter 14 of the Rust book is an overkill. Now, you also don't need an ESP32 because you can simulate it. And anyway, in the first few chapters, we won't even interact with the actual board. So this is not a serious requirement. Though this is a serious requirement, some interest. Because if you don't have interest, then this will be very hard. Okay, it won't be hard, but it will be taxing on your energy. So I'm going to assume all of you guys know what a RAM is, a ROM is, and how the CPU cycle works, the fetch, execute, flow of the CPU, things like those. You don't have to know them in detail, but at least you know the English around it. So those are the that word, yeah. So first of all, are there any questions, any concerns there regarding the prerequisites? So I'm going to assume no questions. Okay. Wait. Yes, Tracy.
Hey,
Hey.
share the GitHub link,
Yeah?
the GitHub repo.
Okay, let me mute myself first. Sorry. Can you kindly repeat the question?
Can you kindly reshare the GitHub repo? Thank you.
Okay, any other questions? So if you have a question, instead of me asking any questions, you just start talking or raise your hand and everything will be smooth. Alright. So, what's a driver? I sat down writing this question, what's a driver? And I also didn't have an answer. Reason being, there are no right definitions in anything. So, any definition used in this book is not the right definition. It's just a definition that was used at that time. So, if you have different definitions of a driver, fine, you're right. If another person has a definition of a driver, blah blah blah, he's also right, they're also right. So according to this page, a driver is a software that sits in between something like a kernel and a physical device. For example, an SSD. So what is a physical device? A physical device, how will I explain it? What's a physical device? Yo, guys, what do you think a physical device is, or what classifies as a physical device? Because I could say this table is a physical device. This cup, this phone, this speaker. So in my view, a physical device is anything that exposes registers and has a little bit of firmware inside. If it's not firmware, then it has an integrated circuit that executes the logic. So that's my definition of a physical device. Now, so a driver is a program that sits in between a physical device, for example a hard drive or a speaker or anything, and a kernel. Now, what's a kernel? I also don't know. No one knows. So, to me, a kernel is a program that is low level enough to write code that can interact with the drive. For example, if you start writing an app right now, you cannot interact with the driver. Even if you use pointers in your code, you cannot interact with the driver. But if you're writing a program that if you use something like pointers, you may be able to interact with the driver, then I can say you're writing something at the level of a kernel. Now, whatever I'm saying may sound confusing. I guess it will make sense as we go. If you have any question, just raise your hand. Now, here is this image being expanded a little bit. So the app makes a function to read a file, and that function is expounded to become a system function. See, a kernel exposes system level functions. For example, sysread, system read file X, and that kernel takes that function, and inside the kernel it converts that function into something that contains driver functions. These driver functions, they are special. They are different from the normal function because they can adjust the addresses found in this physical device. Goja, anyone seeing this image? Do you have any question about this image specifically? And okay, quick question. Is there anyone who has not accessed the book? Oh, how do you zoom screen? Okay, if I zoom it does not encompass the whole image. I think the best way to do it is to view the actual book. Gitonga. Okay, where is Gitonga? Gitonga, can you access the book?
Yes.
Okay, so there is a page there. The image is also there. If I zoom it does not zoom well. So this is just the general architecture. And if there are no questions, then I'll move on. If there are questions that come up, I can go back if you want. Now, how does a driver manage to control the device below? Well, the driver manages to control the device below through two methods, through either of these two methods: direct register programming or memory mapped programming. Now, for those who know what those are, then for the next 5 minutes I'm going to say things you already know. For those who have questions, then okay, me myself, I had time grasping the difference between the two, or just actually doing these two. So it may seem confusing at first. I'll try my best to explain it. If you have questions, yeah. So, as earlier said, an SSD is a physical device. It has storage cells, it has an IC that implements the firmware logic, or it has a firmware that gets executed by this IC or the processor contained in that SSD, and then it has exposed registers. So here's an image. These are the exposed registers. These are the bits of that register. This is a single bit register, an 8-bit register, an 8-bit register. So this image is an image representing an SSD from a very high level point of view, and even it's a fake SSD because 8 bits only. SSDs have like 256, 64 bits, so This one is just a fake image for demonstration purposes only. If we were to implement an SSD at home, this is what it may look like. So these are 4 registers. If you write anything to this register, this processing unit assumes you are trying to do something here in the storage cells that is in, okay, how do I put it? This address is found inside the storage cells. If you have a million storage cells, if I enter here number 8, I will access the 8th storage cell. So forgive my terming there, cells are not viewed that way, but let's just go with it. If I enter number 8 here, I will access the 8th storage cell. Now if I enter number 1 here, or if I enter number 1 here, this processor will interpret it as I want to read the data contained in address 8. If I enter 1 here in the right register, the processor will think I want to write to address 8. Now, if I read from address 8, that processor will go fetch the data and then output it here. So, how does a read operation happen? I supply number 1 here, an input. I supply the address I want to read from. The processor processes that information, fetches the data, outputs it here. So in this case, we will get an 8-bit data. Demonstration purposes too, just. So 8-bit is too little. That's 1 byte only. Let's just leave it that way. Now if I want to write, I will put a 0 here. The electrical signal here, I'll just stop supplying electricity to this register. Then I start applying electricity to this. Supplying voltage. What's the difference? Point is, some wire will be connected here, some live wire with electricity. If I enter here 1 and I register here 2, the processing unit will come and fetch data from this register and try to write this data here in the 8th cell. So I guess the working of this SSD is clear. Kukosa. Yo. Is that the explanation of how this SSD, this fake SSD working? Is the explanation clear?
Yeah.
So like I just said, if I want to write data and I don't have a drive, I don't have a computer, I just have an SSD and a couple of wires and a battery, how will I write the number 5? Okay, the number 1. Okay, I want to write number 1 in address 5. If I wanted to do that, I will take my battery, connect it to a wire, supply electricity to here and here, hence forming the binary representation of number 5 as the address. Then I will supply electricity here to the right register and the data that I want to write, which is number 1. The CPU the processing unit will process it and do a write. That's what I call a manual driver. You don't even have a computer, you just have the driver itself. So how do you automate it using a computer? Enter programming. Here is when the drama starts. You could say, instead of doing this, how about I write code and write it in the RAM. This code should be able to make the CPU okay, let me just find another way to explain that. Initially, you were supplying electricity to these registers, bit by bit. But now, since we want to program it, we can write code that now manipulates how the CPU supplies voltage to these registers. Like, we create a CPU that has this many internal registers, but those internal registers have been directly connected to the SSD registers. I'm having a hard time explaining this. I hope that's clear. So in this case, that program will be stored in the RAM or the ROM here. CPU interacts with it. CPU supplies signals however it sees fit. And that's it. You've managed to write code that manipulates the SSD. That's it. This is what is called register programming. Now, a problem in this approach is that it requires you to have a CPU with this many registers, and in real life that's hard to do. The CPU has limited registers. So a solution to that, people came up with memory mapped programming. And in memory mapped programming, instead of attaching these wires directly to the CPU, you attach those wires to the RAM, like so, and then only a few wires connect to the CPU. So we have solved that problem. You no longer need a CPU with many registers. You can have a CPU with few registers, attach this register to a big RAM, and then from there you can connect these wires directly to the RAM. Now all you have to do is write code. Yes, but this code will manipulate memory addresses. It will manipulate RAM memory addresses. That's what is called memory mapped programming. So I guess that's it. Any questions? Where am I not making sense? If anyone is not following. Okay, so I guess those two things are clear. Register programming and memory mapped programming. So we move on to the next. Now, the driver has two roles. Role number one is to control the physical device, and it does so through register programming and memory mapped programming. Role two is to provide a usable interface. So this means providing an API that the kernel can use. So this API should have things like functions, data structures, message passing techniques there listed. If you're going to implement a protocol above that API, so be it. Point is, provide a usable API above that driver. So those are the main two roles: control and providing an API. So types of drivers. This section is included as a formality. You can write a driver however you want. there's no need to classify them, but people classify them for the sake of being on the same page with each other. So, what are the types of drivers? There are function drivers. These are drivers that don't even care about exposing an interface. Their main work is to manipulate the registers of the underlying physical device. They execute the actual functions. For example, in the case of the SSD, a function driver will just implement things like write function, read function, verify function, checking function, checking for any anomalies in the driver, I think in the SSD or something like that. So function drivers are just as their name says. They're just functions that do things. They don't care about exposing an API. And filter drivers are built on top of function drivers. So filter drivers are the ones that expose more rich APIs, and they can also be the drivers that process data that comes from function drivers. So it's like an upper layer. We have a function driver at the bottom, very close to the device, because it's actually manipulating this device. And then the filter driver acts as a wrapper around the function driver. So yeah, that's it. Filter driver can be about processing data or just exposing a very rich API. Now this other filter driver on top of the other filter driver provides more and more abstractions. Then you finally get to the kernel, then to the app. So I guess that's clear. The difference between a function driver and a filter driver. Okay. So we have now reached the interesting part, which is bare metal programming. So this is the part whereby I will need you to do a bit of writing, a bit of whatever, of doing things. So how many of you have Rust installed in their machines? Okay, let's begin here. How many of you are with machines right now? By raise of hand. So that's a lot of people. That's okay. So how many of you have a Linux? Okay, how many are running Linux, Windows? What's the ratio? Who's running a Linux machine? So Windows. Anyway, this segment does not care if you have any kind of OS. So right now we don't really care which OS we have. In the future maybe we will, but for now this chapter does not care. All it cares about is if you have Rust installed. So I'm not going to assume you have Rust installed, so I'm going to give instructions on how to install Rust. Wait, Ryan, you have a question? Okay. So to install Rust, you go to their page, install Rust. Simple as that. So and then you paste this in your machine. I'm not going to tell you to paste this command. You should not paste commands in your machine from anywhere. But hey, oh man, these are the Rust guys. So.
Sorry, you are muted.
Sorry. I was saying, to install Rust, you visit this page. Yeah, so, and then you paste this command in your terminal, and this one, that command will install stable Rust. Stable Rust is not what we are after. We're after a variation of Rust called nightly Rust. Rust has different versions: beta, stable, and nightly. The features we are going to use are found in nightly. So this command here will help me install just the stable version, but it's a good thing. After installing that stable version, I'm going to give people time. Kuna mtu ana install size first tumtege ama okay, so now we need to install nightly. How do you add nightly? I don't have the command offered, but you can Google it and find it. So okay, you can come to your terminal and be like, hey, wait, say, who has that command? Enter the command here. Assume we can install it. Maybe that command has just slipped me and I don't remember how to do it. If you fumble with the Rust app tool thing, you'll get it. So let's continue. Now there's a recommendation here, the Philip Opperman's blog. This blog is amazing. Why? Because this guy explains things in a simple way. The No-std part, he explains things in a simple way, and I would recommend you to read these 2 chapters there. Now, what do you mean when you say No-std? You mean that you're writing code that does not depend on the standard library. And what is the standard library? Now, the standard library is a bunch of functions that are commonly used by applications that depend on an OS. So you can find that std library documentation by writing this terminal. When you write Rust app doc, you can view this page. It's a documentation for us. There's this link over here. You can open it and you can view the documentation of Rust itself. You can see above here, it's create std. This std is that one for, standard library. It has modules over here, macros, keywords, types, and that's it. This std library depends on this library called core over here. So okay, first of all, there are people who need guidance going through the std library. I can take you through that. I may be saying things you already know, things you already use. It's better if we move journeys. Yeah.
I'm saying maybe somebody's shy.
So now when you wrote your first program. I'm going to assume in C. Okay, some people said they didn't use C yesterday, so let's look at a simple program here. Here's the hello world.
Someone has raised their hand. Brian.
Yo, Brand, Sam.
Vipi?
Yeah, nice.
How did you open those documentation on STD on
How
your
did you?
computer? That tab there of STD Rust.
Oh, okay. I went to okay, so I wrote this command. If you have installed Rust in your machine, if you
Okay.
okay, any other questions? Any other questions? So let's go back. Now here's the documentation for the standard library. As I've said earlier, standard library is a library that has common functions usually used by apps. For example, file system manipulation, printing to the standard output like the console, manipulating memory itself, the heap, things like those. So these are the major modules. There is the allocation module. This one deals with manipulating memory. For example, if you want to allocate memory for a variable or something like that manually, you can invoke this module. Not recommended, but you get the gist. It's about manipulating memory. These ones are irrelevant now. Irrelevant, but they're important. But they're irrelevant now. Yes, they are irrelevant right now. Collections. Collections is a module that contains predefined things like vectors, linked lists, hash maps, trees. So instead of writing these things manually on your own, they have already been implemented for you, and they are found in the STD library. So if you're writing an app and you need a linked list, you can just holler this one. You can add it to your program. Now convert helps you convert between types. That's also important. So far this one, and this one are the important ones to us. FFI will be important within the next few chapters. So right now just ignore it. But FFI is a module that helps you write programs that can integrate with other programs written in other languages. That's just one function of it, a major function of it. There are other functions, but that's the major function of it. It helps you write programs that can be integrated with programs written in other languages. For example, that's how a Rust program can interact with a C program, or a Pascal program, or a JavaScript program. It uses FFI bindings. Now, FS is for file system manipulation. I guess that's self-explanatory. It's a big module, a worthy module, but it won't be of use to us. The formatting, very important to us. It will be very important while building the UART. But for now, know that it's a module that contains functions that help you format data. And in this case, formatting means converting a data type into a presentable way. For example, you can see in these examples, you're formatting something that looks funny to look something like this, to look like this. That's formatting. So formatting is just changing the presentation. It will be helpful for us in the future, but not now. So, and then we have the types. This one's not important for now, but you might want to read them. I have never read them, but okay, you can't just go and read them. Read them when you need them. That's my advice or whatever. Don't task yourself reading this library as a whole. Just read the necessary parts when you need it. So for now, I actually don't need it. So I was just saying we are not going to use this library. We are not going to use std, and that's why we have this name, No-std. Now, the reason we are trying to write a No-std program is because apps written with std library must have an OS underneath, must have a kernel underneath. So if I write an app that depends on std library, that app can only run above an OS, above a kernel, above an execution environment. It cannot run on its own. So if you look at here, if you look here, here's the OS. We are writing drivers. A driver cannot depend on a kernel. It's the kernel that depends on an OS. It's the kernel that depends on a driver. So we cannot depend on a library written on top of this. The std library stands somewhere here. So we cannot depend on something that depends on us while writing a driver. We are the ones who will write things that std library depends on. So we cannot depend on the std library. I guess that point is clear. That's why we are writing No-std programs, because we are the ones writing this std now. So now that we have disabled the standard library, we lose a lot. Like a lot kabisa. Everything becomes awful. Okay, fun. Painfully fun. Okay, nice. Let's just say nice. Everything's become nice. You lose memory manipulation techniques for the heap. Now Rust stops becoming safe when you're dealing with heaps. Reason being, you have to write code that manipulates the heap, you yourself. So that's one disadvantage. So there are libraries that help you do this, but point is you have to figure out how to do it without help from the standard library. Collections, you see those vectors, hash maps, those ones you forget about them, but not entirely. You can use them, but point is by default they are not there. If you want to use a linked list, you will either write it yourself or use some libraries over here, which we'll talk about in the future. But point is, they are not there by default. Stack Overflow protection. What's this? Stack Overflow protection. Now, every program has a stack, and this stack contains values that are being used by the functions being executed at that moment. For example, if I write hello world, there will be a stack somewhere containing functions corresponding to the standard input functions. Hey, how do I put it? Every program is a stack. But now, if I go overboard, writing beyond that stack, I may cause this program to crash. Reason being, the data that I have written could have overwritten another important part of the program. So you have to come up with code that helps you protect someone from writing beyond the stack. In the std environment, that's gone. It's you to come up with it. Now, the init code before main is also gone. This init code, okay, what's this init code, by the way? Now let's take a normal program. Hello world. Hello world has a main function. This one, function main. This function main is assumed to be the first function to be to be executed. But no, it is not usually the first function to be executed. Before this function gets executed, there is like a whole bunch of entire programs above here before this function gets executed. Now, these functions above here do things like setting up the stack, setting up the protection of the stack, choosing which processors to execute the main function, creating threads, creating file systems if needed, things like this. Point is, main is not the first function. Before main, there's a lot of voodoo that happens before it, and there's a standard runtime. Let me just retract that sentence. That sentence will cause more confusion. Point is, you have to write the code before main. You have to think about the thread that calls main. You have to think about the error handling before main. You have to think about the stack initialization before main, and you have to write that code. So No-std becomes more fun. Now, this is I guess it's self-explanatory. Lib-std will not be there because we have actively disabled it. See, that's the name of the thing, No-std, so lib-std will not be there. libco will be there. So what's libco? What's libco? Libco, well, just co, is a library that is not dependent on OS level abstraction. If I write code in libco, if I write code that depends on libco only, I can take that code and run it on a device that does not have an OS. So libco is self-contained that way. To get the documentation for libco, you re-enter this command. You open here. This is the page that opens when you enter this command. So when you open this page, you can see here written core. It's not written libco, but it's just core, and click it. So here is the core library. Now, you can see the first statement says the core library is dependency free, and it gets used by the std library. We have forgotten about this. We don't care about this, but this is what's relevant to us. They have said this library is not dependent on any OS. You can use this library to write firmware that runs on any CPU. Okay, not any, but the point is many CPUs. And core is minimal, and it isn't even aware of the heap. Remember these guys over here where cared about the heap. STD had heap stuff. Core now does not know the heap exists, does not know how to manage it, does not know how to create it. So the core library is minimal in that way. No heap allocation, no concurrency, no input output. Coming back to this init code should take care of concurrency. So no concurrency. Trouble. Now how do you use the core library? How do you use the core library? You use it like any other library. You include it in your document. You include it in your source code. How? Now let's do our first program. Now, to create a new Rust program as usual, or to create a new Rust program, you open your terminal and you write something like, you write cargo name. This one creates a new binary. Cargo new what do we call our program? There. So that's it. Binary. You can create a library, but right now we're just creating a binary. Now created. I open it with a code editor like this. Now, why am I doing this? First of all, I would like to explain these paragraphs over here while demonstrating it. I cannot continue using words to explain this. This one is a heavy set of sentences. They are best explained visually. So that's why I'm trying to write a little bit. Now when you open your cargo project, you see the files auto-generated here. We have the toml file. This file has metadata about your program. For example, which dependencies it depends on, name, version, stuff like this, stuff like that. Cargolock is a file that keeps tabs on the version of the dependencies you're using. For example, if in here you are depending on a library, like which library? Let's say I was depending on clap. Version 2.2. If there's, I don't know if it exists. So in this case, my project depends on the clap library. Cargolock will keep tabs on the version I have put here, such that if I share my program with another person, we end up using the same version of everything. there are no dependency conflicts. So that's the use for cargo lock. It keeps tabs on the versioning of the dependencies. Gitignore is git.gitignore, ignoring target. Target is where our compiled code will be found. And here is our main file, hello world. So let's compile it. To compile it, you run cargo build, the command. Are there any questions? But if you have questions, just raise your hand. I'm not seeing the chats, so or just speak up. Now, just finished. Cargo build compiles it, but it does not execute it. If I want to execute it, I can write cargo run. Cargo run compiles and runs. So there you go, hello world. Now, we were saying we don't want to use standard library. This project by default uses the standard library. Like, there's no need to force programmers to just say use standard library. By default, this thing uses standard library. By default, just by default. We have to force it to stop using standard library. Now, how do you do that? Go to the next chapter. Disabling the standard library. You can find these instructions just in the book. So if I move too fast, or if I don't specify a command well, you can paste it from here. To disable the standard library, you enter this attribute in your code. What's an attribute? An attribute is an instruction to the compiler or to the linker. It's just an instruction of how that code should be compiled or should be. Yeah, generally that's it. There's more to attributes, but that's the definition we can stick to in this tutorial. In this case, there is an instruction that tells our compiler, when you're compiling, don't you dare use std, no-std, and it has an exclamation mark to signify that it applies to the entire crate, to the entire page, the entire. So we go to our program with it and paste it, and then we run. No, let's just build it. Then we get so many errors, and it's let me just clear it so you can see the error as well. So
Hello.
Hello.
There's a question here. If you're recording, where can we get the recording from?
I'll upload them and I will post them in this readme. If you go to the repo itself, here's the repo that you're using. There's this statement here. By tonight, this statement will be replaced by the link to the recording.
Alright.
Yeah.
That's okay. Thank you.
So now we get 3 errors. 1, 2, 3. Now the first error says we cannot find print line number 4. Here it is. Now the reason this error exists is because print line is a macro. Okay, a fancy name for it's a macro. It's a macro found in the standard library, and we are not using the standard library. If you click copy it, and then you come to the documentation of the standard library, and you search that guy, print line. You see, print line is only found in the std library. If I look for the print line in the core library, it's not there, it doesn't exist. No results. So that's why we're having problems. Print line has not been defined. Reason being, we don't have its definition anywhere. So how do we get rid of that, of this error? Sorry. We get rid of it by commenting it out. Oh, I mean, how dare we use things that are not declared? So let's run again. Let's run this code again. Wait, is it clear first of all why? Okay, I'm going to assume since no one raised. Is it clear? Yeah. Now, when you run this again, why is this? Okay, now the terminal. Okay, let me just close it. Sorry for that. Now, when we open, I expect only 2 errors to appear, since we have removed that print line, that unknown thing. Running machine is misbehaving. Sorry. It has been working all day. Be patient with it. So if I build it, I get the 3 errors. I expected 2 errors, but now there. Oh yeah, there are 2. This one and this one. Now bringing me to the other topic. These 2 errors mean a lot, and they have a lot of theory behind them. Oh, they have some good theory behind them. It's okay. We'll go through them now. So we have fixed the first error. But then this fixing of errors, you can find it documented in the book. So if you have not kept up, no worries, you can read about them. Now, fixing the second error and the third error, I would have said there's a lot of theory involved. There's a bit of theory involved. So we go back to the core library requirements. Okay. Here are the core library requirements. Now, when you compile a program, there's this thing called a linker. A linker links objects together. What do I mean? What do I mean? So here's a normal compilation. You take a source code, it gets consumed by the compiler. The compiler does its thing. It produces assembly code and then an object file. I think that's straightforward. Okay. Yeah. Now when you have many files, file A, file B, you compile them, compiler does its thing, produces two separate assembly files, and then two separate object files, and then the linker comes in. It takes those two separate files, separate but related. See, they're related. This one will be a crate for doing X, doing Y, part of application Z. Point is, these two files are somehow related. So the linker takes these two files and combines them. It combines them together in a way specified by the linker script. As you can see, it has not just mashed them together, it has mashed them in a defined way. You define how they get mashed using a linker script. Now let's go back to our dilemma. Now, this first error, and here's that error, panic handler. Let's ignore this one first. Let's ignore this one too. Let's try to figure out what caused these two to happen in the first place. So let's go back. Where is that stuff? Now, the linker, for the linker to combine many files together, it uses things called symbols found in a symbols table. For example, file AC was, okay, let me just open that thing in another place so that it can be seen. These two files are related, but they're different, but they're related. Reason being, file A might reference a function found in file B. So file A might have function, let's say function X, but the definition of file X or function X is found in file B. So A will reference a function found in file B. The reason the linker will now the linker will have to figure out how to connect those two things together, and the linker does that with the help of a table that clearly outlines where the definitions of things are. For example, that table now will contain an entry written file X found in file B, line number 5, blah blah blah. So when A demands file X to be expanded in the object file, the linker will just go to the linker table and figure out, oh, by the way, file X was defined in file B. It goes to file B, fetches it, comes, pastes it in this new file, pastes it somewhere here. So that reference of file X is called a symbol. The linker uses symbols. It uses symbols to identify where things are defined. Now, if we come back here, this library is built on the assumption of a few existing symbols. Now, here is that word. Now, in your object files, you have to define those symbols. So, before we write an No-std program, we have to find a file somewhere and write those definitions of these symbols over here. you should have a file somewhere written memcopy and how memcopy happens. A file somewhere written memmove and how memmove happens. So that's one condition to define these symbols. Second condition of using the call library. Okay, before I got the second condition, the reason these symbols are required is because the call library references them. See, just like I've said here, file A uses file X and file X is found in file B. So file A references things found in file B. Now when we come here, the call library is like file A. It references memcopy function. And now we have to provide file B containing the definition of memcopy. Now the Rust people are good people. If you're using a normal target, those things have already been defined for you. But if you're writing for a custom target, you will have to write it yourself, which you will or not. But I'll lean on the side of, let's just make things easier. You won't write these ones, and that's okay. Now let's go to the second condition. The second condition says that you should define a Rust begin panic symbol. Now this is not a symbol. It's something called an attribute, a language attribute. But for now we'll just call it a symbol. Now you're supposed to define an implementation of this symbol. And what's this symbol? This symbol represents a function that can handle errors. You see, when you call panic, for example, so this is a panic function, a panic macro. It makes our program panic. So now you can see it is written red main panicked at line 5 with the message I am panicking. Now under the hood, panic, when it occurs, it consoles the standard library and it be like, this program is panicking. If it's panicking, what function do we call as a backup, as a handler? We can't just close the program like that. Which function do we call to handle our panicking? So by default, it's just about printing it. That function usually prints the output, blah blah blah. But in our case here, as a No-std program does not know that, it requires you to define that function yourself, that error handler yourself. Now, what is error handling personality? Now there's another issue. Now, panicking does not just happen. When a program panics, it means first of all, the stack is stuck. The stack stops being used. The stack freezes first of all because the program does not know what to do next. It calls the panic handler function to sort things out. Now the panic handler does its thing. If the panic handler realizes, I can't solve this. This is not a normal panic. This requires either the program to stop or to find a more intense error handler. Maybe that, just know that it requires a more intense error handler, or you close the program. Now, personality. What does it mean? If I meet a panic, do I try to solve it? Do I try to unravel the stack? See, the stack has frozen, yeah. But do I free the memory of that stack before closing the program? Or do I just close the program like that? So that's the personality of your program. If your program, when it panics, it just closes everything, it's called a personality of panic abort. And if a program, before it aborts the program, it tries to fix it and start to free memory of the frozen stack, then it's called a panic unwind personality. So, two things. Those things I've explained them in the book, and so I've tried to explain them here, and you can find more explanations here. In the first chapter, like I said, there's a guy who wrote a blog about it, and I really like how he presented it. It was the first material I read when I was trying to understand that topic. So let's just summarize this part here. To use libco, it promises you, I am libco, I don't have dependencies. But the only requirement I require from you is for you to define some symbols that I am referencing. And these are the symbols here. And then in that file that I'm depending on, I want you to tell me how I should react when panics happen. What's my personality? And also, I want you to provide a function that solves the panicking, that handles the panicking. So far, am I making sense? Now, by the way, if I don't explain things clearly, tell me so I can rephrase it. This is my first time, so I'm assuming a lot of things. Are we on the same page, people? Okay, let's move forward. So those are the three conditions: symbols, language attribute, personality. So let's go back to our errors. So we have not defined panic handler, and it's obvious why. libco needs it and we've not defined it. So how do we define it? Come here, and write an attribute there, write a new function, any name. Now let's run it. Now problems. Other problems. Unwinding panics not supported without std. Now you can guess why that problem occurs. But before we guess it, let's go back to this panic handler function has wrong type. Panic handler function by default expects a panic info. What's a panic info? Oh. And also, a panic function should not return anything. In a return exclamation mark, this means this function does not return anything. See, there are some functions return integers, strings, booleans. This function should not return anything. If I call this function, I expect no reply from it. So let's fix this issue first. So it's a divergent function. Divergent function means not returning anything. And if I make it divergent, then I should literally make it divergent. So I make a loop here, an endless loop. Okay, so now we have an endless loop, and now I'm sure this function will never return anything. Now to fix this other error, what is panic info? What is this panic info they are talking about here? And why is it important? So if we go to the core library here, there are many modules. Okay, there are a few modules compared to std, but there are many modules. There's one called it's called what? Where is it? It isn't called panic. Wait, just a minute. Forgot the name. Called panic. There's this module here called panic. Panic support. Okay, it's supposed to be in the core library. These are typo here, but point is the panic. Panic helps you handle panics. Now you cannot use a definition to define, but I hope you get it, get the vibe. So panic info is a struct providing information about a panic. Now this is a panic handler. Before it handles that panic that has occurred, at least provide it with information, and that's what you're providing it, panic information, so that it can handle the panic well. So to use this panic information, we export it to our library, to our text. And here it is, panic info. And now you can come here and pass it. Now this thing should shut up. Oh, it's not shutting up. Let's look at what the error is now. As you can see, this previous error for panic handler imepotea. Sasa hivi kuna moja. Sasa hivi have remained with one only. They are unwinding one. So far, I hope we're together. If I've tried to explain as much as I can in the book, so try to just get a gist of it. And if you have a question, ask it and I will answer it. Now, I hope it's clear why this error message has just disappeared. It's because we have fixed it by writing a panic handler that is divergent and that accepts a valid function prototype. function signature, not product. So let's inspect this error. Unwinding panics are not supported without std, and that's true, because if you look at the core requirements, that's what they said. You need to define the personality yourself. If it's unwinding, provide a function that unwinds the stack. If it's aborting, then tell the Rust runtime that I'm not going to handle errors, I'm just going to panic when any panic happens. I'm going to abort the program, and I'm going to not even care about releasing memory found in the stack. So since we are not going too deep, we are going to take the latter route. We are just going to abort the program. We don't care about releasing memory found in the stack. We're just going to abort the program. So how do we do that? Using nightly cargo, blah 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 blah. Or go somewhere and declare this, and that's what we'll do. We'll declare this. We'll declare that our panic will not be equal to unwind. Our panic will be equal to abort immediately. So let me just go back here. And this thing can be specified in the cargo toml file. You come here, you write this, and you say panic is equal to abort. Normally, by default, it's always like this. Upper it's always written unwind. But now, since we are taking control, we are writing abort. So I'm just going to copy this stuff. And paste it in the toml file. Yeah, so I expect there to be no errors. Or rather, I expect there to be a different kind of error, but hopefully no errors. Okay. Oh, new error. It's a new error. So function main requires a standard library. I think from there it's okay to leave it here. I would like questions, I like suggestions, being that I've just seen the traffic reduce. I'm making it hard for people to understand. So how can we help each other? How can I make it easier for people to understand before moving on? Any suggestions? I was thinking, this may seem like a small chapter, bare metal programming, but it has a lot of theory behind it. Should I take you through it, or should I just provide you a template? Or should you continue doing what you're doing the way we're doing it? I would like people to understand it, and I don't want to rush things. So any suggestions are welcome. At the moment, I just think you can attend the classes, listen to me blabber about things that don't make sense, And then now when you read them, they will start making sense in the background. Yeah, or you can read before the lesson, and then during the lesson, that's when you can start connecting the dots. Any improvement on the book can be made. You can just raise an issue on GitHub. Being that I'm online all day, I'll see it, and I can explain to you during that time. Also, there's ChatGPT. I would just like to make this lesson fluent and easy to understand. So, I guess I can move on. Or should we stop there for today? It's 9:40 and I think I've covered a lot.
Carry.
Yeah?
Let's hear what the students have to say. Maybe a comment, if they were following, if they are understanding. Yes. Ama.
Yeah, really, that's what I expect. Kuna vile sitaki kumislead watu ama kuwa pressure.
Yes. If you have a comment, you can just raise your hand and then you say something. If you can hear me, you can put an emoji. As you can see, Erickson, Janice, thank you, Ryan. So if you have a comment, there's a question here, Kiari.
Yeah, I see a question by Gitonga. So, ESP-IDF hardware access layer is built the same way. Yeah. Okay, not the same way exactly, but with the same principles. They wrote... Okay. Let me just write some. So Gitonga, there's this library called New Library. New Library is a standard library. There are many standard libraries that exist. There's one called MUSL. There's one called the C standard. People say it's the standard. There's one called glibc. Now there's one called newlib. Newlib is a standard library intended for embedded systems, for small devices. So if I take the C standard library and the newlib library and I compare them, newlib will be smaller, it would contain fewer functions. So ESP-IDF is an implementation of the newlib library. Yeah, and to answer your question, yes, that's how it's implemented. Any other question, or before the question you were trying to see the best way forward?
If you have a comment about what Gary is saying, if you want a template than just learning the theory behind this, just say it. Hello guys, can you hear me? Okay, so if you want, we continue like this with the theory. You can just raise your hand. This was it, chapter 1, Kerry?
Yeah, chapter 1.
Okay, I can see one hand. Two hands. 3, 4, 5. Okay, so Kerry, naona like people want to learn the theory vizuri kabisa. You understand?
Okay, now bringing me to my other concern. When I was in uni, there were classes, compulsory classes. And in my head, I used to think, do I go to class or do I stay in the hostels? And my obvious answer was, if I have time to waste, I'll go to class. But if I want to cover content, I'll stay in the hostels and read. So, but then after some time, I started thinking, maybe I can just go to class, hear some new buzzwords, and then when I read, I'll connect those buzzwords in my head slowly. So my suggestion to this is, let's just stick to the theory. I come, I shout some buzzwords, and then you guys take your time to read it, to read the book slowly. And then, if I come to the next lesson, when I start shouting some newer buzzwords, if you have not yet got the previous buzzwords, you can stop me and I can repeat it, or we can go through it together. And that's why I was saying this thing will not take 14 days. In no way are you going to write a driver in 14 days. Yeah? I'm open to extending it for, I don't know, till when, until you're able to go by your own, until you're able to stand on your own feet. So I'm thinking I should take you up to this
If nothing has just speed.
Oh, okay. I'm thinking we can have the theory part in this first 2 weeks, and then we can say like maybe we have part 2 next month. So now part 2 will be hands-on. So the ones who will have gone through the theory and they have gained interest, now they can pick it up from there and attend it the next time. What do you think?
Okay, I think that's okay. So we move on. Now we are here and we have gotten some new errors. Using function name requires a standard library. Now, bringing us back to this statement. When you use a standard library, you do not have when you use the core library without the standard library, the code before main is non-existent. That's a huge thing. It's non-existent. That's why we're getting this error. Using function main requires the standard library because so many things are happening before main and we have not defined them. That's why it's suggesting we use a standard library. And if we're going to not use the standard library, then at least we should explicitly say we are not using main. So that's why it's suggesting we have an attribute saying we're not using main. So I'm just going to paste it here. Now let's just try to run it. New errors. Now I want you to understand this. When you get errors while developing low-level crates, try to read the error messages. They'll help you a lot, more than Googling. Okay, more than asking ChatGPT. Okay, more than. Point is, the error messages are nice things to read, and you will understand them if you got the theory. For example, right now we have seen why this error existed in the first place. It's because we're using the core library, and the core library requires us to define the code before main. That's why this error was. So seeing how these error messages help you figure things out. So now let's examine this new error message. Warning, function main is never used, obviously. In fact, we're going to delete it. Okay, now that warning is gone. So linking with CC fail. What does this error mean? First, I see the word linking, meaning the linker was involved, and the error was with the linker. That linker, that program that combines object files. CC, what's CC? CC is a tool. Can I say a tool chain or a compile? Let's just leave it. I don't know there. But the point is the linker has failed. And note that the errors blah 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 undefined reference to libstat main. What might that mean? It means when the linker is going to the linker to the symbol table, it means that this linker that is trying to link has a symbol table somewhere, and that symbol table somewhere has a reference name called libstat main. Libstat main has not been defined. We are supposed to define libstat main, but where did this name even come from? This name came from the default linker script. Now that's tomorrow's lesson. Yeah, that's where I'd like to end it today. I would like you guys to go through the document and at least reach this error message. Tomorrow we'll start dissecting this error message, because this error message is an entire topic called linking and runtimes. It involves two things: the C runtime and the linker script. So that's it for today. I guess that's enough. That's enough. That's enough buzzwords for today. And if you read the document, there are some references attached. You can read them. Yeah, that's it. That's enough for today. I'm to extend. Let's extend.
That's not today.
No, that's okay. It's okay. It's okay.
So
That's enough.
that's enough. Okay.
So thank you so much, Gary, for that. Guys, tuonane kesho, same time, same link, and kuja na psych. Make sure umesoma what you have learned today, and to make this lesson interesting, try as much as possible to participate, make a comment. So currently, saizi tunaweza, like, you can make a comment on anything, if the lesson was good, if you should be continuing, kitu kaa hiyo tu. Yes, open to comments. You can raise your hand. Anyone with a comment? Oh, Janice gonna suggest if we can be having a short break past the 1 hour mark. Kiara, is that okay?
Yeah.
Like a 10 minutes break, iko sawa? Ama break itashani how long? 10 minutes, okay. Sawa. Anyone else with a question or a comment? I can see Hezekiah Mulene saying thanks for your input. Was this lesson interesting? Okay. It was a good lesson, Janice. Thanks. There being no any other question, comment, I guess I can end the meeting here and see you kesho. Good night. Thanks, Gary.
Poa.
So, see you kesho.